We'll go ahead and get this party started. We are covering 27 and 28, the last two sections. Noah, welcome back. Last two sections should go pretty smoothly after, usually after linear the sections of 25 and 26. People tend to love 27 and 28. So this session today should not take the entire hour. Generally it doesn't, but feel free to ask questions. We should have plenty of time for questions at the end over anything and everything. So if you have them, get ready to ask them. So let's talk about what we do have going on this week. So the last module of new business, last two sections, you do have an Excel assignment that goes with this, and to your happiness, or maybe to you don't care, I did make a video yesterday at the request of a different student of using exponentials in Excel. So I will post that. When I post the live session video for today, I will also post the Excel help video for exponentials, just in case you kind of need a little guidance on how to use those formulas in Excel. You know, that's a 2-minute video that might be helpful for you. So you'll have that. So then you have a quiz, last discussion board, last quiz. You know, you can see the end is in sight. So hopefully you're good to go there. So, okay. Any questions on anything before we get into started and we really get going on this stuff? Nope. Okay, then let's get this party started. So sections 28, notice how here I have sections 27 and 28 on the same screen because they pretty much are the same thing. And you're going to see that as we move through this. So here we go. Exponential growth. I'm going to start with the formula. Okay, now this formula is in words on your formula sheet that you'll get on the exam, but exponential growth in general, and I'm going to use my own variables here, and you're going to say what the H is all of this stuff. Just give me a second, because once you know what all of this means, it's very, very easy. Okay, so this A stands for the end amount, right? How much we're going to end up with at the end, which makes sense because it's all by itself. It's at the end. The I stands for the initial amount. I guess I could have used B for a beginning amount, whatever. It's what you start with. This G stands for growth factor. And we are going to talk about the growth factor more in depth on the next page because there are multiple ways of finding the growth factor. And I want to make sure we have them all taken care of. And then T, as I'm sure you probably can guess, represents time. Now, in this case, time can be any kind of time interval. So days, weeks, months, years, 2-minute increments, 30-second increments, it doesn't matter. Any time period is represented by our letter T. Okay, so really, once you know your growth factor and your initial amount, you can write your formula. So remember, with linear models, we needed a slope and a y-intercept in order to write the equation. With exponentials, we need the initial amount and the growth factor to write the equation. So, okay, that's kind of the formula we're going to use as we move forward. Now let's talk about how do we find that growth factor. So, the growth factor. There are 3 ways to do this. Probably the most common and the one we will use most often is taking 1 plus the percent increase. So if I say, you know, something is increasing 30% each year, then the growth factor would be 1 plus 0.3, because 30% is 0.3 as a decimal, which would be 1.3. So that would be my growth factor. Okay. So that's one way to find it. Another way to find it is to take your new value and divide it by your old value. So if we have something that's increasing, and at 0 it's 40, and after the first year it's 120, let me change color for effect. This would be new, this would be old, because just like with absolute and relative change, new is the most recent. So new is, oh crap, so 120 divided by 40, my growth factor in this random example would be 3. So that's two ways to find it. The third way is just straight up given words. Because sometimes you're going to be told the population doubles. Well, if something doubles mathematically, what do you do to that? What kind of mathematics is involved if you're doubling something? You multiply by 2. Very good, very good. So for growth, for doubling, because you multiply by 2, your growth factor would equal 2. Same concept. If something triples, what would your growth factor be? Times 3. Exactly. So your growth factor would be 3 because when you're tripling something, it's multiplied by 3. So those are basically the 3 ways to find the growth factor. Okay. All right. So now that we have the basic information, we are ready to kind of do some math. And if you have, like, if this all kind of makes sense a little bit, then hopefully we'll be good to go. All right. So let's see how this works. We are going to play with a table. I need a pen. There it is. Okay. So the first thing we're going to do is kind of review absolute and relative change. I crossed out this first one because initially we don't have anything that's old. We just started, so we only have new, we don't have old. So let's refresh just real quick. How do we find absolute change? New minus old, there it is. So absolute change, N minus O. How do we find relative change? New minus old divided by old. Fabulous. There we go. Okay, so I would like you to fill out the table. And so that would be part A. And then see if you can figure anything else out. You should be able to do letter B, but after, or part of letter B. And then after that, you might be stuck. So fill out the table. And when you have that done, give me a yes in the chat box. All right, we got a couple yeses going on. That's good. That's positive. It's positive. Okay. All right. So what is the absolute change in week 1? Let's just run through these numbers. This is a refresher from 23-24. Yep, good. 4, what does that make the relative change? 0.4. Good. Almost didn't see that 0.4. Then we go to week 2. Absolute change for week 2. 5.6. Relative change. 0.4. Absolute for week 3. 7.84. And relative change. 0.4. Excellent. So there's part A. Part B says, what is the same? What do you notice about this table? The relative change is the same. Okay, so we're going to get to an example later where the absolute is the same. And so it's a little bit different of what's all happening here. Okay, so if the relative change is the same, remember, relative change is the same as percent change. That was section 24. And if we have a percent change, so 0.4 is the same as 40%. And that's positive. It's a positive 40%. So what does positive mean in terms of absolute relative change? What's happening if something is positive? We have an increase. Yes. No, I think you're a little bit ahead of us. So at 40%, so 40% is our percent increase. So because we know that we have percent change and this is percent increase, what does it tell you? It tells us that we have an exponential model. That's how we know. We know we have an exponential model because we have a consistent percent increase. Every week we have a 40% increase. So now, how do we find the growth factor? And this is what I think Noah already put up there. Remember from the previous page, the growth factor is 1 plus the percent increase. So in this case, we're going to take 1 plus 40%, which is 0.4, which makes our growth factor 1.4. Okay, so 1 plus the percent increase, and you've got to change that percent increase back to a decimal because we've got to play with it in decimal form. Okay, does that make sense to everybody where these numbers are coming from? Okay, good, good, good. All right, so now, oops, hit a button. Now that I have my growth factor, I have my initial amount, now I can write a model. So I'm going to start with my ending amount equals, what's my starting amount in this problem? My initial amount? 10, exactly. Just like in linear models, when our x value is 0, our output value is our starting point. So our initial value is 10. Inside parentheses, I'm going to put my growth factor, and then I'm going to have my time as my exponent. So this is the exponential model for this particular problem. You'll notice again, just like in linears, we have two variables, the a and the t. Okay. Any questions on how I wrote that model or where it came from or anything? Making sense? Okay. And then the last piece to this says, use the model to predict for week 6. What am I going to do with that 6? Right, week 6 represents time, so we're going to use that and we're going to plug it in for t, right? Yep, it's the exponent, exactly, because it's time, right? Week 6, weeks are time, so we're going to take our a equals 10 times 1.4 raised to the 6th power. Now, depending on your calculator, this should look an awful lot like compound interest, if you remember doing that from section 20. Okay, so we do the exponent first, depending on your calculator, then multiply by 10. And what is our amount in there for week 6? $75.30. Yep. And so again, just like with linears, the purpose of these models is to use to predict future, I don't know, savings, expenditures, whatever this is showing. Okay. All right, any questions about this problem? All right, so that kind of gives us a little bit of absolute relative change review and introduction to exponential. So a little bit of everything there. Okay, now let's come at it from a little more straightforward method. So I'd like you guys to try this one. See if you can write a model in part A and then use that model in part B to predict. I didn't say this was a nice problem, Amanda, but yeah. And this is made up data. I would die if I had that many frogs around because frogs freak me out. Go ahead and give me a yes in the box when you think you might have it. All right, we've got a couple yeses. So frogs are increasing at 32%. So this is our percent increase. We started with 40 frogs around the pond. Okay, so let's start with the model. Remember that when you have a model, you should have two variables in your equation. So what does your model look like for this particular problem? All right, Brooke's good. Ending amount equals initial amount of 40 frogs. She's got her growth factor of 1.32 raised to this t power. Because remember, the growth factor is 1 plus that percent increase, which gives us the 1.32. All right, so after 10 weeks, what do we do with that 10 when we're talking 10 weeks? We plug it in for t, exactly. So 40, 1.32, raise that to the 10th power, and as Vanessa told us, after 10 weeks, you're going to have 642 frogs, which is a lot of frogs. Now, if you have a frog farm, and maybe you're, looking to sell those, or maybe you just want to have a frog leg extravaganza, there you go. This is what you're looking for. You're in heaven. To me, that sounds very painful. Okay. All right. There you go. Exactly. All right. Any questions on that one? That's really a straightforward problem, right? There's your data. Give me an equation. There you go. So it's just being able to recognize that you have a percent increase. The percent increase is what gives you the exponential model. So, okay. So let's move on to exponential decay. So this is section 28. Now, if exponential growth increases, that means exponential decay decreases. It's not rocket science. One goes up, one goes down. So, in terms of our formula, we still have our ending amount, our initial amount, but now we have a decay factor instead of a growth factor. But my friends, let's think about this. So for our decay factor, how do you think we're going to find that? Any ideas? Think about what we did for the growth factor. We took 1 plus our percent increase. So how do you think, oh my gosh, there you go. I didn't have to finish the sentence. 1 minus the percent decrease. Exactly. We're just taking away from 1. We can still do the new divided by old. Sometimes they talk about a half-life in chemistry. That would be a decay factor, that kind of thing. But very, very similar, right? It's just the opposite way of growth. So, okay, let's take what we've learned so far and let's apply that to a table. So again, we don't have to do the first week because there's nothing old. So I would like you to do the absolute relative change and then see how many you can answer on this one, knowing what we've done before. So give me a yes in the chat box when you think you might have it. Okay, we got a couple of yeses, so we're ready to rumble. So let's go ahead and fill in the table. We should be at negative 24, negative 19.2, negative 15.36, and then negative 0.2, negative 0.2, negative 0.2. Right? Everybody agree with my table, or did I screw something up? Because mistakes are known to happen with me. All good?
Agree.
Okay, excellent, thank you. All right, so what's the same? The relative change. Is the relative change always like this? No. We will get to an example in a moment where it's not. Yeah, but for right now, yes. Okay, so in this example, the relative change is the same again, just like it was last time. What does that mean? When the relative change is the same, what does that tell you? Yep, there's your percent decrease. Decrease is 20% every time. And if we have a percent decrease, it means we have an exponential model. Right, so you have to recognize that's a percent decrease because relative change is percent change, section 24. All right, so then how do we find the decay factor? We take 1 and we take away the percent change, right? So 1 minus 0.2, not a negative 1.2, 1 minus 0.2. So our decay factor ends up being 0.8. Because think about it this way. If it decreases 20% every time, well, how much is still there? If you decrease 20%, 80% is still there, right? So your decay factor, your growth factor, those are always going to be positive numbers because they're telling you how much is there when you're done, okay? Good. Okay, so we have our decay factor. How would we write our model for this particular problem? A equals good. Initial amount of 120, decay factor of 0.8 raised to the t power. Good. Again, your initial amount happens when x is 0 or your time period is 0. And then last but not least, how much is left after 6 weeks? So once again, we're going to put a 6 in for t. Because the time is 6 weeks. Yeah, and in this case, you'll notice that we're talking about money, so you really should go to the nearest cent. I mean, I'm not mad. You guys know what you're doing. You got it right, but with web work, pay attention. So you should have roughly 46, I believe, is what it would round to, depending on how you round or when you round. If you take 0.8 raised to the 6th power and you round and then you multiply by 120, you'll get a different answer. So if you're in the ballpark of that right now, you're golden. You're golden. Okay. Did you do okay on that one? Kind of seeing how this is starting to, how the pieces are starting to fit together. Okay, let's go on to another straightforward example. Let's talk about the depressing ownership of an SUV. So give me a yes when you've got this one figured out. All right. We've got so many yeses from different things. I don't know if people are good or if we're just all really agreeable today. I don't know. Okay, so let's start with the model. Who can give me a model for the SUV depreciating 8% a year if you buy a $26,000 SUV? What does our model look like? A equals 26,000 0.92, fabulous, raised to the t. Okay, so this, be careful. When it asks for a model, remember, a model implies two variables. We need an input and an output because this model is for every total possibility that we could have for any time period that we could have. So you've got to have the two separate variables there. Now the 5 comes into play in part 2. All right, so then we have, as Vanessa had there, 26,000.92 raised to the 5th power. Right? And remember that 0.92 comes because we're subtracting 8%, which is 0.08. That's where the 0.92 comes from, for anybody watching. All right, so when we throw in the 5 into the exponent to make it, how much is this worth after 5 years, what do we get? 17,136.12. Yep. Now, and this is an estimate. This is assuming that you don't, crash the SUV and have, huge dent in your bumper, cracked windshield, your cat hasn't thrown up and ripped up your backseat, all kinds of stuff, right? This is general business. Yeah. Okay, any questions about exponential growth or decay with tables or the straightforward problems? Either one of those. Okay, feeling pretty good? All right. Cruising right along here today. So let's do one more table because I know you guys are super enjoying these tables. Again, we're going to get rid of week 1. Okay. Fill in the table, see what you can do, and then, just chill. Give me a yes in the chat box when you think you got something. All right, so we fill in our table. And as you were filling in your table, what did you notice? One, you noticed you were getting super good at absolute and relative change. What? Right. Okay, so we did this, and then we say, okay, absolute value, or absolute change is the same. We know that relative change means we have an exponential model. But those are all different, so we do not have an exponential model, right? Because you have to have a consistent percent increase or decrease, and we don't. However, we go to the absolute change, and the absolute change is the same. So we have a recurring change that's a number over and over and over again. Where? Well, yeah, there's always a however. I mean, come on now. You know that this is the good stuff, right? Vanessa, exactly, it's going to be linear. So we know that if we have a recurring change over and over and over, what does that number represent? What does our absolute change represent in this problem? What is it that is the reoccurring over and over and over? There's a term for that. We talked about it last week. You know what it is. You can feel it. It's in your blood. It's pounding in your head right now. You love it. Maybe you don't love it. Think about linear model. So Vanessa gave us that much, that if relative change is exponential, absolute change has to be linear. Julie, yes, you are correct. We're talking about the slope. Remember when we talked about linear models, we had two things. We had the y-intercept and we had slope. The y-intercept was the starting point. So there's my starting point. My slope is the reoccurring constant change. So when I'm looking at the absolute change, it's reoccurring. Every week, that change is 5. So my slope is 5 because that is the reoccurring change. So because the absolute change is the same, it means we have a linear model and we know the slope. So what is the model? Do you remember how to write a linear model based off having the slope and the y-intercept?
Y equals mx plus b?
Yeah, we are dealing with the y equals mx plus b, absolutely. And then let's go ahead and fill in those pieces. So y equals our slope in this case. We identified that as the 5. So y equals 5x. And then our starting point, remember, is when x equals 0. So that would be 20. So in this particular case, our model would be y equals 5x plus 20. We know it's linear because the absolute change is the same. That's how we figured that part out. All right, so that was part D. And then the last part is 8 weeks. What do I do with that 8? Where does that go in our equation? Plug it in for the thing. Yeah, which thing are we going to plug it in for? X, there we go. Remember, the X always represents the time. So y equals 5 times 8 plus 20. And then it's order of operations. Yeah, so this part's 40, 40 plus 20, and we are left with y equals 60. So for this particular case, you would have $60 after 8 weeks. Yep. All right. Any questions on that one? So we did 3 different table problems today. 1 that showed linear, 2 that showed exponential, 1 with growth, 1 with decay. So hopefully that was meaningful to you. Maybe not, whatever. There are definitely more videos to go with exponentials, so if you didn't get enough from this video, you're going to want to make sure that you check those other ones out. And that's it. So as we are winding down, next week is the final exam. I know it's hard to believe that it's here already. This semester flew. So if you have not already done so, please schedule your exam like now, because remember, not only do we have exam 3, but any online class is taking a final exam next week. So you're going to have to fight for permission. So please make sure that you pick your day and your time, get it done, call today, or do it online today or tomorrow, get that taken care of. Okay. So next week on Wednesday from 12 to 1, I will be available just like I am right now. But there is no session planned. So it will just be open to questions. So anything that you have about the final or the final review or anything like that, bring them. If you don't have any questions, just feel free to move on there. I will grade the final exams as you do them so that your grade will be updated. So you should know, and as soon as the last person takes the final, I will get the grades entered. So they should be done, I would say probably next Saturday at the latest. Is my goal. So hopefully, the earlier you guys take them, the sooner I can do the grades. But you have until Saturday at noon, unless you're taking it in Warsaw, then you have to be done on Friday because we're not open on Saturday. So get that taken care of. Remember, next week your final project is due. If you haven't done that yet, you might want to get that thing done as well. And don't forget you have the quiz, the online quiz for the review quiz, which is fabulous. It's the best prep for the exam that you can do, and you can do it multiple times. So the more times you do it, the better off you're going to be. Vanessa, is your Wednesday question of, is the project due on Wednesday? Is that what that Wednesday is about? Yeah, I don't remember off the top of my head. Let me look. Third project, I have written down 5/9. Is that next Wednesday? Yep. Yes. So according to my paperwork, the project is due next Wednesday. Yes. But again, I will start grading those as soon as they start coming in as well, because I want grades to be done as soon as possible so that you know where you stand, so you can plan whatever else comes next for you in terms of classes or whatever. So as you're working through the end, quizzes, web work, whatever, if you have any questions on anything, shoot me an email, and I will get back to you as soon as possible. So we'll go from there. If there are no other questions, then we're done for the day. But I'll stick around for a few minutes till you all leave. So if you have any other questions, feel free to keep asking. But yeah, it's so close I can taste it at the end. It's nice. It's nice. So thanks for coming every week. Most of you guys are here every week and participating. I appreciate it. It makes my job easier when you do your part. So if there's anything else I can do for you in the next week and a half, let me know. And if there's anything that you think could have been better with this class, I'm always trying to change things to make it better for the next semester. So feel free to shoot me an email and say, hey, it was fabulous, you were great, but this could be better. I never take offense at that because I'm trying to make it better. So let me know what I can do, and good luck on the final exam. Let me know if you have any questions. Have a good weekend, guys.